thin conductive filament is highly conductive. Now to the material that I used is tantalum rhodium 204, so it's transition metal chalcogenide as well. What's important is that it's van der Waals material, which means it is layered, and the layers are connected with weak van der Waals forces. So if we want to create a nanostructure, it's easy to exfoliate. The crystals that we got were around 3-5 millimeters long, and they're thin stripes. And why this material is interesting in the context of my group, which is quantum transport group, is that DFT calculations that were performed on this material show that it's a whale semimetal that contains both type 1 and type 2 whale points. And also it's structural to tantalum iridium rhodium 4, which shows superconducting transition under the pressure. So to sum up, we are interested in this material because of potential to the superconductivity, resistive switching effects, and interesting topology. So first, the first test that can be done with crystal in our group is to just manually contact the microstructure. So we just take the wires and connect them by hands, especially in the context that we had preliminary reports that indicate resistive switchings in C-axis for the macrostructures. So usually in literature, it shows that this is local nanoscale effect, that the reports that we had, they showed that this transition is possible for this material on the macroscale. So we contacted the structure. So in the picture on the right, you can see like the comparison between the real picture and the schematics of the contact that we attached. So we were interested preliminary we were mainly interested in the C-axis transport. Unfortunately, we were not able to replicate the resistive switching on the macro scale, and no significant latent resistance was observed. So the conclusion here is that we need to go to a nanostructure to perform more controlled measurements. However, quite randomly, while we were doing the resistivity tests between different contacts and injecting current in different directions, we were able to find an interesting effect in one of the structures. So simple sketch on the right shows what we expect in terms of voltage distribution when we measure the isotropic structure. And so when we inject current from bottom to top contact, we expect voltage to be distributed mainly homogeneous, except for the middle part of the bulk, and we expect current density lines to be located somewhere in the middle. And we can measure V1 and V2 experimentally, and if for isotropical structure, we expect this relation between them. However, what was observed is that the surface voltage is much lower than expected. So we conclude that the material is highly anisotropic. So it means that resistance in the C-axis is much higher than resistance in the AB plane, which means that the current density lines also spread from the middle. So to have some kind of idea how it looks, I performed a simple numerical calculation for that. So just to see the effect of different levels of conductivity anisotropy. So basically, in the top right, you can see how we define the tensor, or the conductivity tensor, and so with this sigma rising, we can see that the current density lines spread, and the voltage distribution also spreads. So, and it's getting closer to what we measured in the experiment. The issue with macrostructures is that it's not stable and not very reliable. So I was not able to replicate this with the next structure that I made. And obviously the conclusion is the same as in the previous point. We need to move to nanostructure. Unfortunately, due to some logistical issues with lockdown, we were not able to finish the fabrication of nanostructure. But on the right side, you can see the graphite structure that I made probably it's a bilayer. So like for the best takeaway for me from the internship here is that I learned how to do all the steps of the nanostructure fabrication. I learned to appreciate the craft and like how fragile it is. Um, so the next step for us is to create the same structure, but for tantalum rhodium 204. But the issue here is that we will not be able to test anisotropy and the resistor switching effects in this setup because it does not have the z-axis context. So we have the next step after that would be is to create z-axis context in the nanoscale. Basically, we will perform an EVL pre-partitioning for bottom electrode, then we exfoliate or transfer the on top of it. Maybe if you heard if you've seen the talk of Arthur from my group, he's working on he's creating a transfer station that will also be able to help us with this structure, and then we basically do EBL on top for the top electrode. A couple of notes on the tantalum rhodium 204 exfoliations that we already did is that it exfoliates quite easily. The flakes are often layered, so you have to be careful when you like take the scotch tape away because the flakes can be really layered. And we are able to obtain flat flakes up to 20, 30 nanometers in thickness. So yeah, now for conclusion and outlines, we're not able to replicate the reported macroscale resistor switching effects, and we did not see any magnetic resistance on the macroscale. We observed strong conductivity anisotropy, and we did a numerical model for that. So we are now in the process of nanostructure fabrication, and the current task is to do whole bar shape nanostructure measurements, and then the z-axis contact that we not usually do in our group, but we have a few ideas and we're working on it right now. And to finish off, I would like to say thank you to everyone who was involved and helped me during my stay here, in quantum transport group, in material development group that gave us the crystals in IFW, and everyone involved from my home university. Okay. So, thank you.
We are open for questions, also from the faraway audience.
Maybe a comment. So this, what has been seen was a point contact experience.
Yes.
As you know.
Yeah.
And that was being seen on many of these telluric compounds. And therefore, the voltage or the current density which you have was huge. And it's really interesting to see whether this can somehow be reproduced in a more controlled way. Because then, let's say, the whole interpretation in terms of structural phase transition, which has been put forward in February, so a few other questions. So let's say the background, or the scientific question.
If you measure the crystals, would this knowledge interesting under the current structure?
Yeah, sure.
It's usually the theory is slightly modified.
Yeah, I think. But can you compare? But the problem, okay, let's say, motivation for this work comes from Leibniz point contacts. And they can produce metastable states in the same way as you have shown for molecular telluride. So you have, let's say, conductive, or less conductive, and a better conductive state, let's call it like that, in C direction. Probably easier. And that has been seen in point contact experiments now for many different samples, or not samples, different systems. So that's quite interesting. So maybe, let's say, even also this kind of application aspect, because this numbers with switching, but it's not understood at all. So that would mean that there are two metastable states that but different Fermi surface, but different conductivity. So, but I think before we go further, we have first to see whether we can reproduce this in a more controlled way, because point contact always means to check this and here put some pressure and something like that. So a lot of points. So that's the motivation going to nanostructures, trying to reproduce this, getting some large current densities, a large voltages, and then.
Sasha has a question. Sasha, we hear you. I hope.
Because I do not understand how actually you are feeling, how you can hear me or not, because somehow I'm it's it's far from perfect of how I can hear you. But okay, but the question is the following. I wanted to ask about this modeling when you model this distribution, potential distribution. So I do not understand the details, but what would be the difference? This material is topological insulator or not? And what would be the difference between anisotropy and if you just have, for example, surface states much more conductive than bulk?
Well, I don't think that it is relevant within the context of this model because it's very simplistic. It's in room temperature and then just like a conductivity model. When we go to lower temperatures, it will matter, but to be honest, I don't know how to predict that right now.
It has transition to topological surface states, metallic surface state at low temperatures.
Sorry, can you repeat the question?
Maybe I need to mute my microphone here.
Sasha, could you repeat the question?
I think he understood the question. So actually, I understood the answer more or less. But the question was whether one expects that surface states here, the conductivity of the surface state differs from the bulk states, conductivity of the bulk states, and if yes, how it can be implemented in modeling.
In this model, I don't know, because like it's very far from implementing these minute details. To be honest, I don't know what to predict.
Okay.
Yes, like, sure. I can model anything if I have time.
I think at the moment, I think it's anisotropy of the conductivity. I think that's already fine. It's already speaking the experiment that it's free. The idea is that we have to remove them at the highly polarizable and that the large doses could lead to some low unification structure and I think that's the vector. Exactly. We are far away from course, we can really control and understand the switching, then we can also switch topology. But that's something beyond the flow.
So do we have further questions or comments from the audience? Okay. So, but for this part, we thank you again for your presentation.